So far, we've covered the algorithm basis of gradient descent. So it's a pretty simple algorithm. If you are given a function and you want to find out its minima or one of its minima, then you can use this algorithm. And what this algorithm requires is it requires a starting point where you want to, what would be your starting location, what value of x or w do you want to start off with, and it also requires that you can go ahead and calculate the derivative of that function at a given value. So what we need is a function, we need the derivative of that function, and then we need the starting point where we want to start the optimization. Once we have a starting point, then at that point we go ahead and calculate the gradient of that function. Once we have the gradient, we need to take a step in the direction opposite of the gradient, and the amount of the length of the step or the degree of change in the input variable is determined by a parameter that we've called alpha or step size. In this case, we are going to call it learning rate. And why we call that, it's going to become apparent in the coming lectures. Once we have all that, we can go ahead and implement this. On your screen is an implementation of gradient descent in Python. The core of this implementation is pretty simple. It's only a few lines of Python code, and I'm going to walk you through this code so you can understand it better. So what over here, what we have is a function called gradient descent or GD. We have the function that we want to optimize as an input to this function. So this is going to be a function handle. So this is going to be a function handle. And then we also have the derivative of this function or the gradient of this function. So this is another function that gives us the gradient of the original function that we want to optimize. We have a starting value of W, we have the learning rate, so this is the parameter alpha. Then we have a few convergence related parameters, and I'm going to talk about these when I'm going to cover the algorithm itself. And then we have some housekeeping or bookkeeping parameters called history. So I'm gonna walk you through what all of these means when I explain this code below. So we start off with a chosen starting point. We call it W0. So our first value of W is going to be W naught. And then what we do is we calculate the derivative of the function, of the given function at that point, at that W. We multiply it with the learning rate, and then we multiply it with -1 so that we take a step in the direction opposite to the gradient. And once we have calculated that, then what we do is we take that step over here by adding it to the value of W. Remember, this is implementation of the main equation in gradient descent. So the new value of K of W is going to be based on the previous value of W, and then we're going to take a step in W in the direction opposite to the direction of the gradient. Okay, so this is what this implements. So these two steps, this one and this one, implement this simple equation. If the derivative of W is going to be very small, or if the change in W that we want is going to be small, then we essentially uh, stop that. That is, if it becomes too small, then either we are at the optima or and we don't need to update these values any further. So this is the convergence test. Another convergence parameter that we have passed in as input is this nmax parameter. So this loop is going to execute for about 1000 steps by default, or you can change that when you want to specify that function. This is a simple execution of this function. What we have over here is a function that we want to optimize. So this is our f of w function. And then this function is a function that returns the derivative of this function or the gradient of this function. So is this gives the nabla of f with respect to w. Okay, so these two functions are needed. You are going to write them. If you want to optimize this function, then you have to put the corresponding derivative. Let's say if the function that you have over here is w minus zero point 0.5 squared, then the gradient of that is going to be 2 times w minus zero point 0.5. So it's very simple. You have a function of w that we have w minus zero point 0.5 squared. If you take the derivative of that, that comes out to be w minus zero point 0.5, and that's what we have put in over here. If you specify these two functions and you pass these functions as input to this GD function that we have implemented, then that function is going to implement the gradient descent. So this is the gradient function. This is the original function we want to optimize. This is the corresponding gradient. And once we have that, it, this GD function is going to take over, starting from a starting location, W naught, it's going to give us the optimum point or the minimum point of this function by using gradient descent, which is going to be returned in this W variable. It is going to tell us whether it has converged or not. That is whether it has correctly found out the optimal value or not. And it's also going to return some values of the function and its derivative, which we can then go ahead and plot and visualize. So this code over here is simply for visualization. And that's pretty much it. For this particular execution of the function, we have specified a learning rate, or the value of alpha is equal to 0.01. We have set the convergence limit to be 10 raised to the power minus 4. So if your derivative of the function is going to fall below this value, which is pretty close to zero, sorry, to this value, which is pretty close to zero, we are going to say that the function has converged. We are going to execute this function for a maximum number of 1000 steps, and we are going to store history so we can plot this function. So what I'm going to do next is to execute it for you. So let me use the same function that we have over there, which is w minus zero point 0.5 squared, and this is the corresponding derivative of this. If we execute this function in Python, which I'm going to do right now, we get a plot like this, which shows the original function. So the blue line that you see on your screen is the original function. Let me make it bigger for you. On the x-axis is the parameter w, on the y-axis is the value of the function. So in this case, this is the blue line that corresponds to the function. Our starting point on the function is indicated by this the circle, which in this case it's randomly chosen, and in this case it's close to 0.75. And the orange line that you see over here is actually the derivative of this, or the gradient of this blue line. And as you can see, at our starting position, our derivative, or the starting value at our starting point, the value of the gradient function was positive. That means if I decrease the value of w, that is going to take me closer to the minima, and that is understandable because this is a parabola. And you can move from this location to this location by taking these gradient steps. Okay, so you can execute this code multiple times, and each time it's going to pick a random, it's going to use the same function, but it's going to pick a random starting point. If your starting point is over here, then what's going to happen is the derivative over here is still positive, so it's going to decrease the value of w, because that will allow you to minimize the value of the function, and it has not converged in 1001 steps because our step size was probably too small. So if we go ahead and increase that, then perhaps we can converge, right? So let's see. Yeah, okay. So now we have converged to the global optima of this particular blue function. And starting from this starting position, let's take another starting position, and you can play with it multiple times. I'll be giving you the code. It's still chosen the same point. Uh, So yeah, this time it's a different point. And you can, if you start over here at this particular position on W, the derivative of the function is negative. So the orange line indicates that. That means if I increase the value of W, then that is going to lead me to the global optima of this function. And if that is how these gradient steps are determined, now, I have given you this code, and what I'm going to ask you is a series of questions, and I'm going to post those questions. Essentially, they are going to help you understand gradient descent better and the role of each of those parameters. What happens when you increase the learning rate? What happens when you change the function? Let's say if you want to use a different function, let's use this function, let's say. If you use this function, w minus zero point 0.5 squared plus sine of 4w, then the corresponding derivative will also need to be updated. And we have done that over here. And if we execute this, it's going to be a different function. So as you can see, we have a different function. And the question to you is, has it converged to the right position? Is this the global optima of this function? Similarly, you can change the functions to functions of your own choice and try to understand and gain and develop an intuition of how these different parameters involved in gradient descent affect the final output of this algorithm. So with that, I'll be posting the code and you are welcome to try it out on your own. Thank you.